the week before the break, we did introduce psychometric chart. So we need to finish psychometric chart definitely by next week before your test. So I will not be looking at mixing and solution. That will be included in your final. So we will look at that after test 3. After test 3, because or before test 3, because that mixing and solution will be included in your final. So we don't need to rush through that. We just need to finish psychometric chart. So there's 3 questions, but the time is only allocated 2 hours. Like what I said just now, you might not have enough time if you are not very well versed with the calculation. If you are not well, you don't know how to go about it, you might be losing time there. So you really need to know the stuff before you enter the test, before you do your test, because you don't really have enough time. You might be online, you might be having access to the internet, but what I can tell you is that you're not going to have the question exactly the same as that is in the internet. There's no way, they're going to give you exactly the same, and then you just copy and write. It's not going to be like that. So you really need to know your stuff. Okay, so you really need to do a lot of problem at the back of the chapter, and do more and more examples. The one that I haven't covered, maybe you should try that too, so that you really know the stuff. Because there's 3 hours, no, sorry, 3 questions in 2 hours. That's too short. The time is too short. Anyway, let's go to our topic on psychometric chart. So I'm going to share you guys with my iPad. Before that, I need to connect my iPad. Okay. That's good. Okay, now, previously I just jumped into the example, but I realized that I need to introduce what actually we are looking at. Okay, you have this view of the psychometric chart, yeah, the simplified view, and what is going on is that you're going to put it down from 30 degrees C, to 12 degrees C. Okay, so in doing that, you only move horizontally. You only move horizontally from your first location to the second final location. Your first location is your initial position, and you move it horizontally. No mixture, no water vapor is being added. You just move it horizontally to your final location. So that's what is going on when you're cooling it down. So what happened is that when you cool it down, this is your relative humidity. 30. Initially, it was at 30%. You increase the relative humidity from 30 to 80. That's what happened when you cool it down. Okay? But if you proceed to cool it down until it reaches the 100% saturation, at that point, when it is at the 100% saturation, that when you start to have condensation. That's the initial state when condensation occurs at the first drop, which is the dew point. Your dew point is always on the 100% saturation. So you should be able to get your dew point there. This is your dew point, your dew temperature. So if you proceed further to cool it down, you will have to move along the 100% line. So if this is your final position, then you should be able to get the final temperature. It should be on the 100% curve, because there's no other way of going. Once you start cooling it further down, it cannot go anywhere else except on the 100% curve. So that's how you do the cooling. But if it haven't reached the 100%, for example, you are at position number 2. If your final position is at position 2, then the final temperature will be at 12 degrees C. So that's how you do cooling. But if you proceed to pull it down further, then you will hit the 100% curve. And the first drop will form when it is at the dew point. Okay, I'm repeating myself now. So let's go look at one example. We did that last time. We look at example 1. Right, so this is one example that involves pulling. Okay, I have erased what we have done previously so that it is we kind of start part of it. We have done part of the we have taken our point. This is our point. Okay, I mark it using back. That is a point. It is at a temperature of 24 degrees, and 50% relative humidity. So if you look at that temperature and relative humidity, you have to get point, which is that point of interest, the point of interest. So if you want to know the absolute humidity in the full horizontally, you'll be able to get the absolute humidity, which was last yesterday. Yeah, and if you want to get the enthalpy, you just go horizontally, slanting on the slanting line diagonally according to the blue line. You will come out to, let me see, what is that value? Let me erase this. Okay, I erased already the line. Okay, I just want to erase this. Hold on. Let me just partial erase. Like that. Okay, now I can see that. It is 48. So I write down is saturated enthalpy. That's 48. Okay, 48. Just assume it's that around there, around 48. But you have to remember that that is only for saturation. And your point of interest is not saturation. The point of interest is below 100%. So that where exactly is your point of interest? Your point of interest is on the 3%. So where is the deviation? The deviation is, I'm going to use this red line. That is your deviation. That's your deviation. So there's another one over here. It is closer, it is much nearer to the minus 0.2 than it is to minus 0.4. So it's nearer to, the point of interest is nearer to minus 0.2. So we're going to use that value. You can kind of estimate it could be 0.22, maybe 0.24, maybe, but I don't see the significant difference if you get it so exact. It's just rough estimation. So your enthalpy for that point of interest, let's use that. Let's do the calculation. Your enthalpy is going to be the saturated value 48 minus 0.2, which is your enthalpy deviation. We managed to get that 47.8 kilojoules. Please bear in mind that is per kilogram dry air. This is your unit, kilojoules per kilogram dry air. Okay, that's your unit. So that is your enthalpy. So that is your initial enthalpy. So that is the condition when it's enter. This is when it enter. That's the condition. So now the question is, we have done the first part. For the first part, part A, what is the temperature when condensation begins? Condensation only begins when it starts, but that's when it hits 100% curve. So if I go using I don't want to have a black color because it will be it will not be visible on the graph. So let's choose purple. So it should be that location. That is your dew point on the 45. Sorry, on the 100% curve. So this is 15. This where is? Hold on. Somebody correct me. What mistake did I do? Anybody? Are you with me, guys? Excuse me. I'm lagging again. Nobody responding.
Yes, doctor. It was a little bit laggy.
Lagging again?
Hmm.
My God. Let me check the speed of the internet because there's no way it could be lagging because I have the check speed of internet. I have oh my, it's 28, 32, it's 32, because 32. It should not be slow, it's 4K, cannot be lagging. How would it lag? Is it broken? Can you hear me? Somebody? Excuse me, can if I do the video, if I do the video, let me see, if I do the video, okay. Is that better? Now that I do the video. Quite bad. Why is it bad? The speed is 32 megapixel. How could it be bad? Oh my God. What's happening then? Why is my voice lagging? Now it's better. Okay, good. Because just now I off the video. Is it better now? Anybody respond, please?
Yes, better, doctor.
Good. Okay. I'm not going to use the video then. I'm not going to have the video on. Okay, so the speed now is 32. Somehow the video is causing it to lag. Okay, now let's go back to what I was telling you guys just now. I made a mistake. What mistake did I make? Somebody comment. What mistake did I make when I was showing you the psychometric card? Anybody? Nobody going to respond? Nobody? Okay, I was talking about the dew point. How to get the dew point? Anybody?
Draw a horizontal line
Horizontal line, and then
toward the saturation line.
yes, 100%. So it should be the dew point should be around there, not the one that I marked here. This is wrong. That's wrong. Okay, so it should not be that. That is not the dew point. Yeah. So the dew point is 12.8, but the solution gave a value of 13. The dew point is 13 in this solution. Give you a value of 13. That's close enough. We get 12.8. That's very close. So now the second part of the question is the rate of heat transfer that must be removed when you have 1 meter cubic of humid air entering your unit. So what we're going to do is we're going to draw our block diagram. Every time you have something like this, you need to draw your block diagram. Okay, this is your block, your unit. You have 1 meter cubic coming in of humid air. I forgot to draw this yesterday. That's why I made a mistake. And this is your outlet stream coming out. Your inlet stream, you have the value of 24 degrees C and 50%. 50% relative humidity. Okay? So your outlet stream should be at 100% relative humidity. Why is it 100%? Because that's when it starts to condense at dew point. This should be at the dew temperature. If you use the 13 degrees C, then we use that. You can use the 12.8, no problem. Okay, so this is your unit. The question asks, what is the amount of heat that you need to remove? Should be going the other way. Should be removed. What is the amount of heat? Kilojoules per second. And that's the question. Okay. So now we need to get the enthalpy. Just now we have the enthalpy. The enthalpy we got just now, this is the enthalpy in. We need to get this enthalpy out. Right? We need to get that enthalpy out. So that enthalpy out, you should be able to get it at the dew temperature, at the 100%, the dew point. So if we say it is 13, then it should be somewhere there. At that point. So if you read it from the dew, from that line, you extend it. Okay, what is that value then? 36.5, something like that. Is it 36.5, guys? Is it 36.5? Or is it 37? Guys, I hope we are okay now.
36.5.
Sorry, Ibrahim.
36.5.
36.5, thank you. 36.5, thank you. Okay. It's still lagging, is it? Okay, so we make do with what we have. I'm surprised it's still lagging because the speed that I have shown on my screen now is 30. Keep on unstable. The speed is unstable. Right now it's 35, 36, I mean 35. Okay, anyway, that's the entropy of the outlet. The entropy of the outlet is 36.5. 36.5 kilojoules per kilo dry air. Okay. So now we're going to do our energy balance. So I write the entropy here because I need space. Equals to 47.8 kilojoules per kilogram dry air. I don't know why am I having problem with the internet because it should be okay. It's 35. That's very fast. Okay, now your energy balance. If you do your energy balance, the equation. If you write the equation for the open system, you write the whole equation so that you cancel out anything that needs to be cancelled off. You can say cancel out. Sorry. So there's no turning parts. There's no change in height. There's no change in velocity. So you end up with your Q is equal to the change in the rate of entropy, and that is equal to out we are using mass flow rate. We haven't calculated the mass yet. Minus in. We need to calculate the mass because the value given is in 1 meter cubic, so we need to get the mass. We managed to get entropies for in and out. We need to get the mass. Okay, now I need to point out this out. Please take note. It's very important because your calculation will be based on per kilogram of dry air, as your entropy is based on per kilogram of dry air. So you need to get the mass, which is this mass, and that mass should be per kilogram of dry air. It cannot be the total mass of the humid air. It's just the dry air. So how to get that? Let's look for the volume because this is in volume. That is for humid air. Okay. So we need to get the volume of your initial air and in the air. So what is the initial volume? I have drawn here in green. The line is dotted green that I have over here. So if we extend that, okay, let's say that's about 1, 2 intervals. Okay, that's about 2 intervals. So it start from here. Let me expand that. Okay, that start from here and it ends here. That's 2 interval, and 1 interval we already said is equal to 0.857 times 10 to the power negative 3. We have calculated that a few times already. Yesterday, in fact, we did that. So you got 2 intervals, so 2 times 0.857. Oh, it's lagging. I can see the writing is lagging. So that will give you a value of, we did this calculation actually yesterday. I don't know why it's lagging. The net internet is 35, it should be okay. 1.714 times 10 power negative 3. That's about 0.001. Okay, so you start from 0.85. It should be more than 0.85. So that value of your volume, your humid volume, is going to be 0.85 plus 1.714 times 10 power minus 3. And that will give you a value of 0.85 meter cubic per kilogram of dry air. Because your unit should be the same as that unit here. That is your humid volume. Please bear in mind, it's the humid volume. That means it includes water vapor plus dry air. So now let's go back to the question itself. The question said that I'm going to have 1 cubic of humid volume coming in. We need to find the kilogram of dry air. Why? Because your enthalpy is based on per kilogram of dry air. So you need to find that value of kilogram of dry air. So we're going to change that 1 meter cubic of humid volume to kilogram dry air. So what we're going to do is 1 meter cubic of humid air. You have that humid volume just now. Your humid volume is 0.851 meter cubic of humid air per kilogram of dry air. It's a bit slow. I can see it's lagging. Okay, so now you can cancel your meter cubic. You end up with your kilogram of dry air. So if you do the calculation, I'm going to do it here. 0.851 inverse get 11.7. Sorry, not 11. It's actually 1.175. That's the kilogram of dry air coming in. That's the kilogram of dry air coming in. So if you jot that down on our diagram, that's going to be where I'm going to put it. I'm going to erase the volume. I'm going to erase this volume. I'm going to write down the dry air. Okay. So this is going to be 1.175 kilogram dry air. And what do you think will be the outlet amount of dry air? Anybody? Anybody? What is the amount of dry air in the outlet stream?
I think should be the same, right?
Yes, it should be the same because dry air is still the same. Should be the same. Okay, so now we are done. You can solve your energy balance. So since the amount of dry air is the same, we were going to take out the amount of dry air. We're just going to have bracket your out enthalpy out, specific enthalpy minus the specific enthalpy in. So we have the amount is still the same for the dry air, so we take it out of the bracket. So let's do this down here because I need a bigger space. So that's your amount of dry air, your enthalpy out minus your enthalpy in. Okay, so your amount of dry air just now is 1.175 kilogram of dry air, and multiply that with the specific enthalpy of the difference of the enthalpies. The outlet is 36.5. That's 6.5. I'm looking at my diagram because that's the where I jot down my enthalpies. That's my enthalpy for the outlet. Yeah. My enthalpy for my inlet is 47.8. That's 47.8. So I just write down the unit now. That's kilojoules per kilogram dry air. So the reason why everything is per kilogram of dry in terms of kilogram of dry air is because we want to cancel off the kilogram of dry air. So if you do the
second.
Sorry?
Is a rate. Second per second.
Per second. Oh yeah. Yes. The meter cubic is per second. So it should be per second. Thank you very much. Your voice is also broken. It's really bad. I don't know why it's bad because it's 35 megapixel. So it should not be, is it megapixel? BPS per second. Okay, so that's per second. That's per second. Okay, change our unit. It should be in terms of rate. So that's per second. So your answer, the final value will be in kilowatts. So I don't think I have enough space to write that. So I'll just put it down here. Okay, let me erase that. Okay. So now if we do the calculation, I will do it over here. 36.5 minus 47.8. That will be minus 13.278 kilowatts. That's the amount of heat that you need to remove in order to cool it down until it reaches the dew point. That's the amount of heat you have to remove from your system until it cools down. This is actually like an air conditioning unit. You cool it down, the temperature of the inlet air, until it drops to the dew point. That's when you start having drops of liquid coming out. Okay, so that's the amount of heat that need to be removed. So that's the second part of the question. So let's look at the third part. Sorry. Now, if you're going to further cool it down till 10 degrees C, what's the fraction of water that will condense? And what's the amount of heat that you need to remove for the same amount of 1 meter cubic of humid air? And so now, instead of going to, before this, we did it until 13. Now we're going to change that 13 to 10. So that means you are going down. If you look at the complete chart, you'll be from 13, you'll be going down to 10. So this is what happened. That is your value of 10. That is your 10 degrees C over there. So you are moving along the 100% curve till you reach 10%. So at that 10%, if you locate your enthalpy, okay, so what is that value? That's about 29.5. That is the enthalpy for the 10 degrees C saturated in outlet. The outlet stream is saturated and it is at 10 degrees C. So because it is beyond the dew point is when it started to condense. You have the first single droplet form. But because you cool it down you cool it further till it reached 10 degrees C, that means there will be more droplets forming, more condensation. So you will have water coming out from your aircon unit, your unit now. So we will draw the diagram. It will look something like this. Your block diagram, it will be slightly different. Just now the amount of dry air is still the same, 1.175 kilogram of dry air per second is still going to be the same. Why is the amount of dry air not changing even though you are condensing? Because dry air is just dry air. Your water vapor is the one that is condensing. So there will be water coming out. This will be the amount of water, kilogram per second of water, liquid water, condensing. Because it's liquid, it means initially it's in the state of vapor, but it condenses and becomes liquid. So let's jot down what we have. Okay, so this is 10 degrees C, saturated. Or if you don't want to write saturated, you just write 100%. The relative humidity is 100%. Okay, so the amount of water coming out is also 10 degrees, sorry, not the amount of water. The temperature of the water coming out is also at 10 degrees C. Why is it at 10 degrees C? Because it's coming out from the same unit. So it should be the same at the same temperature. Your initial value is 24 degrees C, and your relative humidity, if I'm not mistaken, is 50, is it? Let me look at my diagram, 50, yeah, 50. And your initial enthalpy is 47.8. 10. Your enthalpy in, specific enthalpy in is 47.8 kilojoules per kilogram of dry air. Yeah. And you need to find the enthalpy of the outlet air, and you need to have the enthalpy of your water. Yeah. This is enthalpy of your air. This is enthalpy of your water. And so we will do it using a table as we always as we have been doing so far. Let's construct our table. Hold on, we will have a table. We we will have our substance, which is A and water. The water is going to be a liquid water because that's the one coming out, not the vapor. Okay, so we will have in M in, that will be in kilogram per second. Our enthalpy in, that will be in kilojoules per kilogram. We have M out, that will be kilogram per second. And we have our enthalpy, specific enthalpy out, again kilojoules per kilogram. Okay, that's done. So the amount of water coming in, there's no liquid water coming in. The amount of A, it should not be the humid A. Even though coming in is humid A, but you're going to write just the amount of dry A. Why is that? Why is that, anybody? Why am I writing the amount of humid A? The amount of dry A, not the amount of humid A.
Because that's what's going out.
Yes. That's not because that's what's going out. No. It's coming in as the same as the one coming out. That's not the reason.
Because we have it in dry air, not in humid air.
Yes, because your enthalpy is given in per kilogram of dry air. Your enthalpy is per kilogram of dry air. You will also get this kilojoules per kilogram of dry air. So in order to cancel out your kilogram of dry air, you need to use the unit or the value of per kilogram of dry air. Even though your air coming in and out is humid, it's not it's not dry, completely dry. It's not 0%. There is 50% and 10%, 100%. So there's humid air there. There's water vapor in it. But the reason we are writing in putting in the value of this just the dry air in our table is because we're going to multiply it with the enthalpy. The enthalpy has a unit of per kilogram dry air. So you need to cancel out that kilogram dry air. So let's put in the value. That's 47.8.
Doctor,
Yes.
since we have water vapor in the inlet, can we use saturation tables to calculate the enthalpy for them?
You don't need to. You already have the psychometric chart. You just need it in terms of per kilogram dry air.
So we ignore the enthalpy for water in the inlet.
Your enthalpy is actually the enthalpy of the humid air. It's actually the enthalpy that include the water vapor. Why? Because have a look at the psychometric chart itself. Let me show you the one that is in the notes. The enthalpy is that of the humid air, but the unit is per kilogram of dry air. The unit itself is the one that is per kilogram of dry air, but the enthalpy itself is that of, where is my enthalpy chart? Yeah, this is it. The enthalpy itself is actually, where is my, I'm going to look at my, there, see? I'm looking at the reference. Actually, I need to look at it. Not that, okay. Reference state, liquid water, 1 atm, dry air, 1 atm. Degree C. So, the liquid water is already included in the enthalpy. Sorry, the water vapor is already included in the enthalpy. When they do this graph, when they plot this graph, they already include liquid water. I mean, they include already the water vapor, but the reference state start with liquid water. Okay, so does that explain? Okay, good. Thank you, Aiman.
Clear, Doctor. Thank you.
Okay, good. So now let's go back to our example. So the enthalpy that we get here for the inlet and outlet is already inclusive of the water vapor. So you don't have to find for the water vapor. It's already inclusive. So that is the enthalpy for the water vapor. The humid air, but it's just that the unit itself is per kilogram of dry air. So this will be per kilogram of dry air. So I'm not going to write it down because it's understood. Okay, so the amount of I should not use that. The amount of dry air coming out is also the same. Yeah, so kilogram dry air. The reason I'm writing this because your actual value should be the coming out air should be humid. But the reason why we're writing it just in terms of dry air, because we want to cancel out the unit of the enthalpy. So now the enthalpy out. We need to find the enthalpy out for the humid air. So let's go to our psychrometric chart. We are now, just now we managed to get it, isn't it? 29.5. So that is the outlet enthalpy of your humid air, 100%. That's 29.5. So let me write that over here, 29.5. Yeah. Next, for water. How much water is coming out? Do we know? We need to calculate it. We don't know the amount of water coming out. So we need to do a material balance, which is we need to calculate the amount of water using the water balance. So first thing first, what is the amount of water vapor in your inlet? Anybody know? What is the amount of water in your inlet stream? You know? We have over here, if you remember yesterday, we have, this is kilogram of water vapor per kilogram of dry air. So this is actually the amount of water vapor in the air. Yeah, I'm going to erase that because I want to show you guys. We say it's going to be 0.092. That is the relative the moisture content or absolute humidity. So let's get that done. Let's get that written over in our board diagram. So our absolute humidity for the inlet is 0.0092. Again, you write down the unit in terms of per kilogram of dry air. So this is per kilogram of water vapor per kilogram of dry air. So for your outlet, you do the same thing. That is in. So your outlet, your absolute humidity out. Going to use the psychrometric chart to get the value. So we are now here at 10 degrees C. This is your 10 degrees C. So I'm going to use a red ink in order to show it so that it will be visible. I'm going to get a horizontal line going to the y-axis. Oh dear, I'm not doing a good job there. I should zoom out first. Okay. Get a horizontal line with the y-axis. Is that okay? Is it straight? Okay, more or less straight. Okay, so what is that value? 0.00775 roughly. Anybody dispute with that value? I estimate it to be 0.0075 roughly. Okay, you don't have to get it that exact. So that
Yes,
is
Doctor.
thank you, Nabila. So that is your amount of water in the air coming out. So 0.0075. Is it? That's what I got just now, isn't it? Yeah, 0.0075. Why is it less than the inlet value? Anybody? Why is it less than the inlet value? The inlet value is 0.092, but the outlet value is 0.075. Why is it less than that?
Part of it has been condensed.
Yes, thank you very much. That's part of it has been condensed. Your water has been condensed. Your water vapor has already condenses. So now we're going to calculate that amount. How much of that water condenses out? What's the amount of water that condenses out? So do our water balance. Just water. Yeah. Okay, so we have 1.175 kilogram of dry air coming in. We need to get the water amount of water vapor, so we multiply that with your absolute humidity. Kilogram of water vapor per kilogram of dry air. That is your absolute humidity. So you cancel off the dry air. Yeah. Is equals to the amount that is coming out in your air. Your air is still 1.175 or dry air. Multiply with your absolute humidity, 0.0075, the value that we just got just now. That is the amount of water vapor in your A per kilogram of dry A. Cancel that kilogram of dry A. Okay. So next we have plus the amount of water vapor that is condensing. That is the kilogram of water liquid per second. There should be per second over here, per second over there. Okay. So as you can see, you should be able to solve for the unknown, which is the amount of water that condenses out. Take out the 1.175 kilogram. Take it out from the bracket. So and then we just get the difference between the value of the absolute humidity. That will give you your kilogram of water per second condensing. Can you calculate that?
Yes, 2 times 10 to the negative 3.
2 times 10 power negative 3. Thank you, Aiman. Okay, so that's the amount of water that condenses. So let's see whether is there an answer given for this problem. Oh, okay, the answer is given. The answer given is 0.17. Sorry, the answer given is 0.176. We got 2, 0.2. We got 0.2.
I got 1.975 times 10 to the power negative 3.
Oh, 1.75.
1.99.
1.99. Well,
Yeah.
approximately 2. Okay,
Yeah, just
approximately 2. So that's a slight difference. Why is there a slight difference? Because of the value of your absolute humidity that we read off from the graph. Because everybody have a way of estimating it roughly. It's a rough estimation. How you read it off from the graph. So nobody can get it exactly the same. Everybody will have a different value of a small amount of difference. So that's why there is a slight difference. Okay. So that's the value of the amount of water coming out. Okay, so any questions? We have one more part to solve, the amount of heat that need to be removed. We just now, well, for part B, we did the calculation for the amount of heat, but that was initially at 13 degrees C. The outlet was at 13 degrees C. So now we have condensation occurring, and we need to calculate the amount of heat. So let's do that. Where is our diagram just now? This is our diagram. So we need to calculate the amount of heat that has to be removed. So you do the same energy balance. The same energy balance, except that now you need to find the enthalpy of your water. So if you look up your appendix, table B5, let me unshare this so that I can show you the appendix. Oh no, I have my appendix here, if I'm not mistaken. Let's see whether I have my appendix. Oh yes, I do have it here. Let's find appendix B5. Okay, the temperature of the water coming out is 10 degrees C. So we'll be looking at a column, the first column to be in terms of temperature. This is temperature, that's nice. That's the temperature. We're going to look for the enthalpy at 10 degrees C. So this is 10 degrees C. So we're going to look for the enthalpy, which is 42. That's the value of your enthalpy, 42 per kilogram of kilojoules per kilogram of water. Yeah. Guys, what happened? Nothing happening? Can you see? It's 42. Okay, so I'm going to jot that down. Okay, I'm going to jot that down, it's 42. So I'm going to go back to that example just now. So our water, the enthalpy of water is 42 kilojoules per kilogram. Okay, so now write down the amount of water that we have obtained just now, 2 times 10 to the power negative 3. So 2 times 10 to the power negative 3. That's per kilogram per second. And your enthalpy is 42. So we have completed the table. Now we just have to solve for the amount of heat that you need to remove. Again, you do the full equation of the energy balance. You need to write down why you cancel the terms that need to be dropped off. You need to write it down. Why? You need to give a reason. So don't forget about that. Oh, another one more thing. I haven't done the basis and the reference date. I need to remember that too. You guys also need to do that. So after this, we'll be writing it down. Okay, so your Q is equal to the change of enthalpy, the rate of change of enthalpy. Again, you have the out, the mass flow rate, and the specific enthalpy, the inlet, the mass flow rate, and the specific enthalpy. Right? So taking, we cannot take out the mass flow rate because we have water, which have a different flow rate. So now, looking at your table, that's my table. Yeah, I have the outlet. I need to, okay, I have the whole view now. I have my outlet of the A times by its corresponding enthalpy plus that of water that condenses out, that's the liquid water, plus the corresponding enthalpy. So that is your outlet stream minus your inlet stream. Your inlet stream is the amount of dry A times by its corresponding enthalpy. So that is your outlet product. So you should come up with an answer. The value should be kilojoules per second. When you do that calculation, anybody going to get, are we going to get the same answer as the solution? Let's see, look at the solution. Solution is 21.32. I don't think we're going to get the same because our value of enthalpies are slightly different. So let's just check the calculation, please. Let me see, let me do the calculation. Minus 37.8 plus, okay, it's minus 21.42. That's what I got. 21.4185 actually. Yeah. Minus. Why minus? Because we are removing heat from the unit. So it should be minus. So you are cooling it down. So that's the amount of heat removed for the system when it is being cooled down to 10 degrees C. So the answer in the solution is 21.32. We managed to get 21.4. Quite different due to the value of your enthalpies and the absolute humidity. So any questions, guys? Any questions? Okay, I over here the chat said, somebody said, oh, that is minus 3211. What is that? Minus 13. Somebody gave me a value. Oh, that is that Q. The first part is minus 13. So for the last part is minus 21.42. Any questions? Clear? Good. Ibrahim saying that is clear. How about the rest of you guys? Any questions? Because you really need to understand how to solve using psychometric chart, how to solve energy balance, because that's one question. Out of 3, that's one question coming out. I have no idea how in what format is coming out. I hope it's not going to be in English unit. Hopefully it's in SI unit. I don't like English unit, but the principle is still the same. The technique of solving is still the same. Yeah. So the other 2 questions will be just single phase. That means there's no change of phase. And the other one is multiple phase. So every time you have multiple phase, either condensation occurring or boiling occurring. So that's the typical question for change of phase. Any questions, guys? Any questions?
Yes, Doctor, just one question.
Yes, Ibrahim.
If I have a mixture has been cold or vaporized, and I want to construct hypothetical bath for this mixture, what would be the normal boiling point for the mixture as whole, not for every individual component?
Well, if it's a mixture, it's very difficult. It's very difficult to get the boiling point of a mixture because your appendix, they are all given for single component.
So I have to construct one by one.
Yes. Remember, we did an example that have, I think we did a few examples on that.
Yeah.
We have mixture.
Yes, but I just wonder if there's like a way to get the average normal boiling point for the mixture.
No, that will just make it more complicated. There is a method to estimate it, but that it will just make it more complicated. It's easier if you use the data in the appendix for individual components.
Okay, ma'am.
Okay, thank you, Ibrahim. Any other questions? Okay, now we are done with this example, so let's look at more examples. But before that, take 5, please. It's already 2:52, so be back here around 5 minutes later. Okay, guys, take break, 5 minutes. Okay, guys, I'm going to unmute myself. Hey guys, welcome back. That's a short, very short 5-minute break. Anyway, let's have a look at another example. This is an example that's almost similar to what we have looked at before, except that the values are different. Okay, so you have A coming in at 1 atm, 30 degrees C, 80% relative humidity. The rate again is in volumetric flow rate, 10 meter cubic per minute, and it leaves saturated at 14 degrees C. So part of the moisture in the air will condenses out again at the same temperature, 14 degrees C. Calculate the rate of the heat that need to be removed and the amount of water vapor that is going to be removed from the air. So the answer is given over here. So let's see whether we can come up as close to that as the answers. Okay, so let's draw our block first. Oh yeah, guys, I need to remember. I just forgot. I just remember. I need to write down the basis and the reference state just now. For this example, write down your basis. What is your basis? So you can use the basis, which is 1 meter cubic per second, which is that value of humid air. You can write A or humid air, doesn't matter. Okay, your basis. Remember the basis and your reference state, because you're using the psychometric chart, the reference state should be the same. So your reference state is going to be the same as that of your psychometric chart, which is dry air, 0 degrees C, 1 atm, liquid water, 0 degrees C, 1 atm. Okay, so we need to write the same as that of the psychometric chart, because your enthalpies that you got just now when you do the calculation, they are from the psychometric chart. So the reference state must be the same as that of the psychometric chart. Okay, do remember that. I almost forgot about that. So let's go back to that example that we were going to solve. And again, your basis. The basis will be the amount of flow rate given, which is the volumetric flow rate. That is your basis of A coming in, okay, or entering or fit. Okay. So let's draw the block diagram. This is your A coming in, 10 meter cubic per minute of A. Humid air, that is humid air. So you can write humid air if you want. Your temperature is 30 degrees C. The pressure is 1 atm. The relative humidity is 80%. Coming out, the outlet air will have a temperature of 14 degrees C. It is saturated. Okay, it is saturated, it's mentioned there. And you will also have water condensing out. So that will be, let's give it a value, a symbol of M subscript water, kilogram per second, per minute, because the unit is per minute of water, liquid water. That's your block diagram. So definitely going to have amount of heat being removed. So we're going to calculate that in kilojoules per minute. That's your amount of heat coming out. So we're going to solve it exactly like as how we did before. We need to find the enthalpy of the A. Let's give it a symbol this time, H1. Specific enthalpy, that is H2. And for your water, enthalpy of water. Okay, your water is also coming out at 14 degrees C. So you can use the appendix B5 to get the enthalpy of your water. Should be in kilojoules per kilogram. This also should be in kilojoules, sorry, not kilogram, kilojoules per kilogram of dry air. Over here, kilojoules per kilogram of dry air. Okay, so now let's start using our psychometric chart. Your inlet is at 30 degrees C. So zoom in, 30 degrees C. I'm going to use a different color. Okay, 30 degrees C, that's 30 degrees C. I'm going to draw a straight line. Hopefully I can get a straight line. Can I get a straight line? No, I'm not getting a straight line. Can't do that. Okay, that's straight. And the percent relative humidity now is 80. I'm going to look at 80%. Oh, I haven't reached 80 yet. This is 80. So I need to go further up. Okay, that's 30. Okay. Let me undo this. Okay. I need to do a better job. This is 80. Okay. So this is my line. Okay. So if you zoom in, so that's more or less where the intersection is. That's the point of interest of the inlet. So if we read the enthalpy, all you have to do is project it up with the enthalpy scale. So what is that value? That's about 85.5. That is for saturation. Now we need to find the deviation, the enthalpy deviation. Where is the enthalpy deviation? And to use a different color so that we will not be confused, blue in color. Where is the enthalpy deviation? So this is the enthalpy deviation. That's minus 0.1. Yeah, the other one is minus 0.2. That's 0.2. That's 0.2. So where are we exactly? About midway between 0.1 and 0.2. So I'm going to say about minus 0.15. So this is the point of interest. Yeah, it's about midway, roughly. So that value of the saturated enthalpy is 85.5. 85.5. So we're going to get the enthalpy for the inlet. Let me change that to black. This is going to be, I don't have enough space there, so I'm going to write it here. 85.5 minus 0.15. So if you calculate that, let me use my calculator. Should be 85.35 kilojoules per kilogram of dry air. So I'm going to write that over here, 85.35. So I'm going to erase my calculation. I'm going to erase this. That's how I get my enthalpy for the inlet. Okay, so next I need to do the same thing for the outlet. The outlet is at 14 degrees C. I can know where 14 is because all the 100% saturation curve, that's 10, 11, 12, 13, that's 14. So it should be there. So if I project my, from that point to the scale, the enthalpy scale, I should come up to a value of what? It's about, that's 40, that's a 39 point something. 39 point, let's say 39.3 maybe. Okay, let's just give it a value of 39.3. Let's put in that value 39.3 in our block diagram. That's 39.3. Okay, so that's your enthalpy for the outlet stream of your A. And the enthalpy of your water, again, we're going to use the appendix from table B5. Our temperature, outlet temperature is 14. So where is 14? This is 14. Sorry, I should not be using that. That's 14. So where is our enthalpy? 58.8. Okay, the enthalpy of liquid water at 14 degrees C is 58.8. So I'm going to use that value and write it down in our block diagram, 58.8. So let's go back to our, where is my example? Okay, that's 58.8. So I'm going to write that down, 58.8. So everything is there, the enthalpy is there. The only thing that I need to find is the kilogram of dry air. I should have a value from this volume. I should be able to calculate the kilogram of dry air. I need to get the volume, the specific volume of the humid air. So our location just now is here, location of interest is there. We need to get a straight line, diagonals or slanting or parallel to the green line. So I'm going to use a green line, but this time I'm going to draw it using broken line. Yeah, so to the point of interest, through the point of interest going to the x-axis. So that is the point of interest. Parallel. Is that parallel, guys? Not parallel. Is it parallel? Let me undo this. I need to get a parallel line. Not straight, is it? Is it straight? Well, that's the best. So now I'm going to estimate what is that volume. I'm going to change it to black in color. Okay, so just now this is how many partition do I have? 1, 2, 3, 3.5. That's about 3.5. 3.5 times, remember that value just now, what is the value? The value of the interval that we have calculated earlier. We have a value of 0.857 times 10, that's the value. 0.857 times 10 to the power negative 3. How do we get that value? I hope everybody is, you know how to get that value, 0.857. Anybody doesn't know how to get that value? This value, 0.857 times 10 negative 3. Anybody? Please voice out if you find that if you don't know how to get that value. Please ask. Anybody? Are you guys with me?
Doctor,
Good.
can you show it again how to
How to get it? Okay.
yeah.
Okay, let's count. 1, 2, 3, 4. Intervals. Count the interval. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Remember, it's about 17.5. 17.5 intervals is for the distance from it's not the distance, from the value of 0.85 to the value of 0.09. So that is these intervals, the intervals that we have for for the difference of 0.09 minus 0.05 plus 0.05. So one interval is going to be 0.05 divided by 17.5. So if you calculate that, you should get 0.857 times 10 power minus 3. Or, is it the same?
Right.
Yeah, that is the value of that one interval. So now, just now, this is, let's zoom in. I have, okay, I'm going to erase this. I don't want to have too much of, yeah, so if I project that down, okay, now I have one interval, I have two interval, I have three interval, that's 3.5. That's 3.5. So I multiply 3.5 with that value of the one interval, I should be getting, what should I get? 3.5 times 0.857 times 10 to the power of negative 3. That is equals to 2. It's approximately 3.0 times 10 minus 3.
Doctor,
Okay? Yes.
it's 0.05 over 17.5, right? I got 2.857.
How did I, hold on. What interval? How come I got wrong? 2.857. Oh dear. I thought it should be 2, isn't it? Let me look at, did I jot down wrongly? Where is my examples now? It should be 2, isn't it? Should be 2, not be 0.57. How come I got 0.57? Where did I get that value, 0.57? Okay, let's go back to the example just now. Do you understand what I'm trying to do here, guys? Should it be 2 or should it be 0. Do you understand what I'm trying to say? I'm doing now. I have between 0.85 and 0.9. The interval there is 17.5 interval. So for every one interval, what is the value of one of the interval? How come I got 0.857?
Doctor, you're trying to interpolate, right?
Yes.
So if you want to interpolate, then you have to calculate the distance
I did.
from 0.85.
Yes.
So it's that number minus 0.85,
Yes.
I think.
0.9 minus 0.85. I got that. Isn't it?
Yeah, but doctor, when you do that and then you divide by the total number of intervals, you get 2.857. I got the same.
2.857. So I
Yes,
first,
doctor. So first, we count how many intervals. So there are 17.5 intervals, right?
yes,
So suppose, where's the point?
the point is somewhere here. Yes, the one
So
that
we count that. That's around 14, I think.
okay. So I'm
that's
going
around
backward.
14.
I'm doing it backward in reverse from 0.9. Now just now I got it wrong here, isn't it? It should be 2. It should be 2, isn't it? So that means this one should be 2, isn't it?
Yes, 2.857.
Okay. So the previous example I need to correct it. It should be 2 then. 2 then, isn't it?
Yes.
Will it make it any different if you calculate that value? Will it be any different? Different, slight different. 5.714 times 10 minus 3.
I think that's why we got a different answer.
I guess so. I guess I made a mistake there. Please correct the calculation. These guys, I made a mistake. Somehow I missed the 2. I got 0. I don't know how I got that it becomes 0.587. But somehow I got the 0.857 correct. So now let's do the calculation. So now I'm going backward. I'm doing, if you want to go forward from 0.85, okay. If you want to go backward from 0.9, it's the same thing. Okay. So if we multiply this, I'm doing backward. So it's the same thing. You're going to get the same answer actually. Let me see what I'm doing now. 3.5 times 2.857 explanation minus 3. You will get 9.99. So I'm going to erase this value. I erased that one. I'm going to be 9.99. That's going to be 10. 10 times 10 to the power of negative 3. So that's for this distance. So what is the volume then? The volume will be 0.9. I'm going backward. Minus 10 times 10 minus 3. So if you go forward, you multiply it with the distance, which is about 14. I'm going backward, time by 3. So 3.5. So it's about the same. You will get 0.890. Did you get that too? If you go from 0.85? Anybody? You do the same thing. If you go from here, from this point, going to the dotted, the dashed green line, that's about 714. So if you do the same thing, 14 intervals. If you look at this dashed broken line, the broken line green color, that's the 12, 13, 14 intervals. So you multiply with 2.857 for one interval. You will get what? Let's do the calculation. About 0.04. So you multiply that amount, 0.04 plus
Same, doctor, same.
0.85. Same, isn't it?
Same. 0.89.
Yeah. So you can do it either way. If you're from 0.9, you minus that value. If you're from 0.85, you plus that value. You will still get the same value. So that is your volumetric humid volume. Specific humid volume 0.89. So we need to write that down. 0.89. I don't know why I got 0 just now. I mean the interval, but you get the idea how to get the interval. This is the kilogram dry air. Okay? That is the humid volume. What it means is that is dry air plus water vapor. That is the volume occupied by the humid dry air, the humid volume occupied by dry air and water vapor. That's what it means. Okay, so now from that value, I'm going to erase that. From that value, we're going to get our dry air. So we have 10 meter cubic, which is that value. 10 meter cubic per minute. You divide it by that humid volume. Because you want to change the meter cubic per kilogram dry air. You will cancel off the meter cubic. You will have kilogram dry air per minute. So if you do that calculation, 10 divided by 0.890, you will get 11.2 That's the amount of dry air. So the amount of dry air is the same coming in and out. So I'm going to write this over here, 11.236 kilogram of dry air per minute. Let me tidy up. Please. I need to tidy up. Okay. I'm going to erase this, erase that, erase this, and erase this. Okay, so now that's better. That will be kilogram dry air per minute. The same amount coming in. Why is it the same? Because nothing is dry air cannot condense. Okay? Only water vapor can condense. So you have that amount of dry air. So now what we're going to do next, we're going to write down our reference state because we're going to do our energy balance. So your reference state must be that of your psychrometric chart because you obtain your enthalpies from that psychrometric chart. So dry air at 0 degrees C, 1 atm. Let's make sure that this is the correct reference state. Let's go back to the notes. Okay. Liquid water, dry air at 1 atm, 0 degrees C. Liquid water at 1 atm, 0 degrees C. So now it's confirmed. That is the reference state. So you have liquid water at 0 degrees C, 1 atm. That's your reference state. So we're going to do construct our table. We have two rows. Your substance. This is air. It should be humid air, but the problem is you're not going to write the humid air, the amount of humid air. You're going to write the amount of dry air. Reason because your enthalpy is per kilogram of dry air. And this is your water, liquid water. Yeah, so this is the amount of air coming in. Sorry, the amount of flow rate, kilogram per minute. What happened here? Kilogram per minute. Yeah, your enthalpy in, specific enthalpy, kilojoules per kilogram. And your amount of flow rate out, kilogram per minute. And your enthalpy out, kilojoules per kilogram. And done. So now your amount of air is not the whole total amount. It should just be the amount of your humid air. Your dry air. It's 11.236. Same amount in, same amount out. And that's the amount coming in and out. And there's no water coming in. Your amount of water coming out, we haven't calculated that yet, so we need to do that calculation. The amount of water that condenses. The same thing last how we did the calculation for the previous example. So let's do that. Do our material balance on water balance. Okay, the amount of dry air, 11.236. That's the kilogram dry air per minute. You need to get the absolute humidity. Sorry, the absolute humidity. That's it. HA. You need to get HA here. The absolute humidity for the inlet and the absolute humidity for the outlet. So how are you going to do that? You need to go to the psychrometric chart and read it from the y-axis, which is your absolute humidity. Okay, let's do this slowly. Where is our point of interest? Our point of interest is up here. So I'm going to use red in color, and I'm going to use, red in color, a solid line, draw horizontally, straight line. Oh, not really. Okay. Something like that. It's about 0.0216, 0.0216, roughly. That is your initial absolute humidity, 0.021. Let me get black marker, 0.0216 kilogram water vapor per kilogram dry air. That is your inlet absolute humidity. Your outlet absolute humidity, do the same thing. Where was it just now? It was at 40 degrees C. That's our outlet condition. I'm going to then use a red ink point projecting horizontally to the y-axis. I need to zoom out. Don't really need to get a straight line because it's already 0.010. You can read it off from the graph itself. It's already there's already a horizontal line there at that 14 degrees C. So it's 0.01. Let's get it written down here. 0.01 kilogram water vapor per kilogram dry air. Done. So now you can get the amount of water by multiplying the dry air with that of your absolute humidity. So now your absolute humidity, let me get that 0.0216. 0.0216. That's the inlet. Yeah, that's the inlet. Kilogram water vapor per kilogram dry air. We cancel that off. We get the amount of water coming in. Is equals to the amount of water, the amount of dry air again, multiply with the relative humidity of that outlet. Just now we say it was 0.010 kilogram water per kilogram dry air. So this is per minute. Don't forget that minute. So plus the amount of water vapor, the amount of, liquid water coming out. That's kilogram of water condensing. So if you do this, that's your on the block diagram. Coming in is one stream, going out is two streams, so you have two outlets. So that's what I have written over here. I have two outlets, I have one inlet. So what I can do, I will solve for my water that condenses is 11.236. Bring that out because both of them have the same value. 0.0216 minus 0.010. We will come up with a value of, let me calculate that. Anybody managed to get faster than me? I got 0.1303 kilogram water per minute. That's the amount of water that is coming out. Guys, you get the same value?
Same, doctor. Same.
Thank you. So let's check our solution. Let's see. Okay, a bit different. The answer is 0.1. It's very close actually. 0.131. We managed to get 0.330. Sorry, 130. That one is 131. Now we're going to calculate the amount of heat. The answer here is 511. Let's see whether we get the same. Most probably not, because our enthalpy is, how accurate can you get your enthalpy from the graph? It depends. Most probably the author get it differently from our values. So Q, you do your energy balance, your equation. Remember, you need to write it full. Then you need to cancel out the terms that need to be dropped off. And then you need to give reasons why you are dropping it. Okay, so whatever terms that need to be cancelled off, give a reasons. Yeah. So your Q again is equal to the change in the enthalpy rate, and that's going to be out the mass flow rate times by the specific enthalpy. Your in the mass flow rate times by the specific enthalpy. So now let's look at our table. Have we finished everything? Yes, we need the value of our water that we just calculated just now. And the enthalpy that we got for water, we did look it up in the appendix. That is 58.8. That's 58.8. What enthalpy did we get for our inlet A? We got enthalpy 85.35. Inlet 85.35. For the outlet, we got enthalpy 29.3. Okay, now we are done. You just need to calculate the energy balance. So I need to zoom out because I need to see the whole table. Equals to 11.236 times by its enthalpy 39.3. I'm looking at the outlet. My plus the amount of water that the condenses with its corresponding enthalpy. That is the outlet minus the inlet. which is 11.236 and by its enthalpy. That's done. Okay, so just multiply it. We should be getting our answer in kilojoules per minute. Let's do the calculation. Anybody manage to get the answer?
I got negative 509.76.
Yeah, same with me. Okay, that's the answer for the amount of heat that has to be removed in order to cool it down from the initial temperature to the final temperature. So let's see. The value given by the author, he managed to get 511. We got 509. So not bad. It's just a difference of slight difference due to the amount of the enthalpy that we read off from the chart. No, it's just by visual. You estimate it by visual. So there's no way everybody going to get the same value. So this is how you do it. The same as that previous example we did. Exactly the same procedure. Any questions? Any questions? This is one of the typical example. You need to calculate the amount of water that condenses. Excuse me. This is just like an aircon unit. When you pull down the air, you condenses out the water. That's what you see outside of the house in the outlet pipe. There's water driplet, dripping from your pipe. That is the liquid. The water vapor that condenses when you cool down the air. That's what actually is happening in the air conditioning unit. This really just bear in mind. Please bear in mind that this is actually the dry air, the value of the dry air, the amount of the dry air. You cannot have the total flow rate. This is really, really critical. And you really need to know how to get this humid volume from the graph. Just remember that you need this interval. This is the value of one interval, for one interval. If you can write that down, just use it anytime you did the humid volume. It's very fast. Any questions? No questions? Everybody okay? Is it still lagging?
No, doctor.
No.
Okay, I realized that if I on the video, that's taking too much data. So I really need to off the video. So from now onward, I guess I just need to off the video. Okay, now let's look at, I'm not going to solve the whole thing. I'm just going to point out to you guys how we're going to go about it. This is one example. Everything is very similar. You need to find the absolute humidity. That's the symbol HA. Why do you need the absolute humidity? Because when you want to find the amount of water that condenses, you need that absolute humidity. Next, you need to find the dew point. Well, the reason you want to find the dew point is condensation starts at the dew point. You don't really need the wet bulb temperature, but this question asks for wet bulb temperature. You need the humid volume. Why do you need the humid volume? Because if your question, the amount of, for example, in this case, 2000 meter cubic per hour is the amount that is coming out. In this case is slightly different. Your outlet air is 2000 meter cubic per hour. So from that amount of meter cubic air, 2000 meter cubic per hour, you need to find the humid volume of the outlet, not the inlet, because that's the amount that is in the outlet stream. Okay, so from the humid volume, you should be able to get the dry air, the amount of dry air. But the one that you're getting over here, the humid volume that you're getting over here is actually for the inlet. So that you cannot multiply it with that humid volume. That is for the inlet. Because the question asks for the outlet to produce. That is the outlet. So you need to find the humid volume of the outlet. And how are you going to find the outlet? Well, you have a temperature of 20 degrees C. So you should be able to get the humid volume at 20 degrees C. Yeah? So it's cooled down to 20. Why do you need to know the dew point? You need to know the dew point because let's look at the dew point. The dew point is 26.2. If we look at the solution given here, the dew point is 26.2. Your final temperature is 20. So that means if you draw the graph, this is your dew point, 26.2, but you are cooling it down further to 20. That's 20. Okay? So that is your final outlet condition at 20 degrees C, not at 26.2. So the condensation will occur because it's further cooling from the dew point. If you cool it down at dew point only, condensation only one drop. Only one drop. It's not significant, just one drop of water. But if you cool it down further to 20, you will get a certain amount of water condensing. So that's the reason why it's further cooled down. Okay, so get this for the outlet, which is meter cubic per kilogram dry air. So if you multiply this with that value, you should be able to get your kilogram of dry air. The outlet amount should be the same as the inlet amount. That is the amount of kilogram of dry air. Should be the same. Okay, this is in, same as kilogram of dry air out. Should be the same. Same technique of solving the problem, except that it's a slight twist. A slight twist because the questions give you the volumetric flow rate of the outlet instead of the inlet. For the past two examples, we have been given the flow rate, the volumetric flow rate of the inlet. For this case, it's the outlet. So that's how this, just a slight twist to it. Okay, from that amount of volumetric flow rate and the humid volume, you should be able to get the amount of kilogram of dry air in and out. So after that, after you have done that, then you go to part C. You solve for part D first, then you solve for part C. Or else you can't solve it. Can you? Actually, yeah, you need part D first. You solve part D first, then you solve for part C. Because you need the kilogram of dry air. Okay, so for this problem, it's exactly the same as the previous two examples. Not exactly the same. The procedure is the same. It's just that there's a small twist to it. You do part D first, and the volumetric flow rate is that of the outlet, not the inlet. Any questions? No? Guys? Here is Kuda is getting darker. We're going to run soon. Okay, if there's no question, we're going to look at a different part of, we're going to look at our notes. Okay? Anybody, any questions? No questions? Okay, I'm assuming that everybody is here about the two examples. So now we're going to look at the thing is slightly different cooling, but actually the only difference is that you go horizontally from a lower temperature to a higher temperature. That's what happened in heating. Just now we were looking at cooling. When we did cooling, we go the reverse direction. Okay, that's cooling. So let's see. Going to look at another topic, which is adiabatic cooling. In the textbook, there is a topic on adiabatic cooling, or there is referred to as adiabatic humidification. The topic is 8.4c. Okay? So adiabatic implies that there is no change of heat between the surrounding with the system. That means Q is equal to 0. That is adiabatic. Right? So when you are having adiabatic cooling, actually what happened, you have a hot air coming in, then you spray in water droplets. You spray in liquid water droplet through this spray, and what happened, the liquid water that is being sprayed will be evaporating. It's the reverse of what happened just before this. It's the previous example we were looking was condensing. Now the water droplets is spray into the hot air, and that water droplet will evaporate. So when it evaporates, it becomes water vapor. So you have water vapor. Initially, it's liquid water. So when you spray it into a hot air, you vaporize the liquid water into vapor. So your outlet will be moist. You will have a moist water air. So let me highlight that. This is moist. Okay? Your air will be moist. So actually what you're doing is you're making it humid. You have a hot air, making it humid, which is reverse of what we are doing just now. Okay? So how to go about it? If you look at the psychometric chart, initially you're at 0.1. That's the initial position. So if you spray liquid water into the system, your system will not move horizontally. On the psychometric chart, it will move on the diagonal line, which is that line of your enthalpy line, to the final position or the final condition, which is denoted as 2. So when you're using adiabatic cooling, when you're dealing with adiabatic cooling, you have to move it on the wet bulb line or the enthalpy line. This is the enthalpy line. It's the same as the wet bulb line or the wet bulb line. It's the same thing. If it's not exactly on that line, then get a parallel line to it. Okay? It should be on the slanting line. And if you want to read the enthalpy, you just projected it up to the enthalpy scale. That will be your enthalpy. So your enthalpy does not change. It's the same at position 1, at the inlet position and the outlet position is the same. Your enthalpy doesn't change. The only thing that changes is that the temperature drops from this initial temperature to the final temperature. There's a drop in temperature. Why is there a drop in temperature? Because your water vapor evaporates. So when it evaporates, it's just like how I'm going to explain this. It's just like a heat exchanger. The hot air get cooled down, and the liquid water absorb the heat from the hot air. So the water evaporates. So the hot air become cooled down. So it's just like a heat exchanger. In fact, here in Malaysia, you have this sort of system. If you come across some restaurant, they have a very huge fan whereby you have water droplet being sprayed into the fan, and that cool down the air. That's actually the same principle here. Okay? So this is actually adiabatic cooling. So if you look inside your textbook, the strap look like this. This is the diagram inside a textbook. Yeah, your liquid water is being sprayed. Your hot air is coming in. For example, in this case, your hot air is at 30 degrees C. Now it's going to be cooled down. There's no mention of what temperature it is, but it's going to be cooled down. This is the outlet air coming out, cool down. Initially, the humidity is 10% because you spray water into it. The liquid water evaporates. There will be more water vapor now. So the humidity now increased to 40 degrees C. Instead of 10, now it increases to 40 degrees C. But this is the same principle. Some of the water might come out as liquid because of that is the excess water that did not evaporate. But normally you will ignore this part. Yeah? Normally you will have enough water, just enough that all of it evaporates. Yeah, you don't have any excess liquid water. Just enough. Everything will evaporate. So this is how you go about it. So not sure that I have enough time to cover this, but let's see what happened in adiabatic cooling. Yeah? Just go through the theory, and we will look at the example next Sunday. Okay, so now the enthalpy is constant. Just highlight it. The enthalpy is constant because H1 equals to H2. Your wet bulb temperature is also constant. How you get the wet bulb temperature is when it is at the 100% saturation. That is your T wet. Yeah. What else? Your dry bulb temperature decreases from T1 to T2. It decreases. Your dry bulb temperature decreases. Your humidity ratio increases. Let's have a look. Initially, This is, for example, this is 10%. Now that's increased to maybe 80%. Yeah, so increase the relative humidity. Why is it increasing dew point? The dew point, of course, increase. Why is the dew point? The dew point is a horizontal line. Oops. The dew point is a horizontal line. So that's projected that. That is the dew point. So here, that is your dew point. Dew point 2, dew point 1. So that increases your dew point. That increases your dew point. Okay, you guys getting out already? Let's see. Anything else? There's no loss of or gain of heat within the system. Just like I mentioned just now, it's just between the water vapor, the liquid water, and the hot air. That's just how the heat is the change of heat. There's no loss of heat loss to the surrounding. Okay, your water, let me write it here. The amount of heat will be even the hot air will heat up the liquid water. The hot air will heat up the liquid water until it evaporates. Once it evaporates, you will get a moist air, but cool down. Your hot air is being cooled down because the hot air supply the heat to the liquid water, which causes the liquid water to evaporate and increase the amount of water vapor in the air. So your air will get cooled down and get more water vapor, get more humid, get more moist. That's how the principle works. There's no loss of heat. There's no Q going to the system or no Q got lost to the system. Okay, guys? Any questions on this? We will look at an example, more examples next week. We will not look at mixing and cooling, mixing and solution, because this will only be covered in the final, so it will not be covered in the test in test 2. So better not mix it, and I don't like to rush through because you have your second test coming soon. We need to pay more attention to the psychometric chart and the calculation of entropies for the single phase and the multiple phase. So I don't want to rush through. So we will continue doing more examples. We need to find the adiabatic saturation temperature. We will need to find the adiabatic saturation temperature. It's about the same principle using the adiabatic. In this case, you have water. This water will evaporate. You will get water vapor. You initially have an unsaturated air. You end up with saturated air as the outlet. So what is the adiabatic saturation temperature? You can find it from the graph. Okay, any questions? We will not look at an example now because it's already 3:50. Almost, sorry, no, it's 3:45. If I start looking at an example, I don't think I can finish it. Better start fresh on Sunday. Any questions? Nobody? Going to ask anything? Guys, are you still with me?
There's
Let's
a
see.
question in the chat box.
Oh, yeah. Doctor, if it's a closed system, are we supposed to look at the chart? Does this system represent throttle, doctor? Throttle actually is a release of pressure. You increase the pressure and you reduce the pressure, throttle valve. Throttle valve is you release the pressure. I mean, you reduce the pressure. Let me get it right. Is it reduce or increase? Throttle valve. Guys, check it out. Throttle valve. You check it out. I might be wrong because I think it should be reducing the pressure. I'm reducing the pressure. Throttle valve is reducing the pressure. Okay, the second question is, if it's a closed system, are we supposed to look at the chart? Typically, if you're looking at a psychometric chart, you'll be looking at an open system because you're looking at adiabatic cooling. You're looking at condensation, which is an aircon unit. It could be a closed system if you have a closed room. If you have a room that is For example, you have one room whereby you don't have any air coming in, no air going out, then it becomes a closed system, just a room. Can be a closed system, but typically it's not a closed system. Even though you are cooling the room in the air, your air is coming in from outside. The compressor is sucking in the air from the outside into the room. So it cannot be a closed system. It's an open system. Yeah. Any other questions? Anybody? Initially, I have 33 students, 2 already left. Now it's 31. Anyway, guys, yesterday I do apologize. I don't know what happened. The internet somehow was unstable yesterday. I went to N01A, but I cannot get a cable. It's not that I cannot get a cable. I cannot get an internet through the cable. But I managed to get Wi-Fi, and Wi-Fi was not that good. And I have to stop by 9:40, if not mistaken, 9:30, because I ran out of my computer, my laptop ran out of power. That's why I just have to stop there. Anyway, it's not worth it going through the whole process if the internet is not that good. So any other questions? Okay, so if the air is humid, but it occurs in a closed system, then the table to find out the internal energy. That's normally, just like I said, normally it's very difficult to find a closed system when you're dealing with air, because the air is most of the time is going to be sucked in. For example, cooling down a room, it's actually the air from the outside coming in. So it's very difficult to have a closed system. Most of the example is an open system. You will not come across a closed system. Very, 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 very difficult to find a closed system. Any other questions? I'm not sure whether it's it's not that it's rare to find a closed system, but majority of it is open system. So you will not be asked on a closed system. Any other questions? Nobody? By next week, I hope we can do more examples, especially on adiabatic cooling. There's a few examples here that you can try to do it yourself and see if you get the same answer. I got the answer written there. Yeah, I got the answer written for some of the examples. We did this example just now. This example for heating. Is it heating or is it cooling? This is slightly different. You humidified it. So maybe you should try to do that during the weekend. The answers are there. In fact, you can get it from the internet. If you look up, you search it in the internet, you should be able to find the same exact question, and you should be able to know how to do it. But try it first, and also try more problems at the back of the textbook. Okay, guys. I'm the one who's going to set the question on the single phase and on the double phase. So I have already already set up already got it set up. What I can say is this: both of the questions actually involve heat transfer. Sorry? Yes? I can't hear you. Did somebody say anything? No? Okay. Since there's no other questions, just like I was saying just now, the test. Okay. Both questions that I have set, I might change my mind, but right now, one of the question is on heat exchanger. Yeah. The other question, I have an idea what I'm going to ask, but I haven't solved the solution yet. I might change my mind if I find that it might be too long, or it might be I can get a better question than that, or I might change my mind. But one of the questions I'm going to ask is on heat exchanger. Right? So that's one of the questions. The psychometric chart will be set by Dr. Jamaroliza. She also have a rough idea what she's going to ask, but she haven't set the question yet. Because we will know definitely by next week what's coming up. Okay, guys. So thank you very much for attending the online lecture. Do apologize about the internet, the lagging. But most probably it's because of the data is too high. The data for the video is too much. Maybe that's the reason. I hope after this we'll not have any problem with lagging or broken voices. So I hope everything is fine. Okay, guys, take care. Now it's going to rain over here. And for anybody, wherever you are, take good care of yourself. Stay safe. And see you guys next week online. Okay, guys. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Doctor.
Thank you, Doctor.
Welcome. Most welcome.
Doctor,
Okay. Yes.
can I have the attendance again, please?
Okay. Let's see. Where is the attendance? Oh, it's raining quite heavily. It's going to rain. Okay. Can you scan it?
Okay, Doctor, done. Thank you.
Okay, thank you. Most welcome. Take care.